Hello, my name is Scott Hatfield, and I'm a chemistry teacher, and I may be your chemistry teacher this year. Welcome to chemistry. This is the first in a series of videos that I will be posting on my class blog that quickly summarizes important material that may not always be covered in your textbook or which may go along with material that comes with your textbook. This seems to me like a very efficient way of covering a lot of material and making sure students can go over the material as often as they need to. So again, welcome to chemistry, and I hope you'll take advantage of these videos on a regular basis to deepen your understanding of the material in this course. Science investigates the natural world. And science assumes, but never proves, that the universe follows laws of nature. Now, when we say that we make this assumption, a law of nature is believed to be something that's always true everywhere all the time. But in point of fact, we can't actually look everywhere in the universe, and we can't look at every time in the universe. So we don't actually know for a fact 100%. We can't actually prove that there are laws of nature. But it does seem likely that there are, because there are things that no matter where we look or how far back we look in the past, because when you look at an image of a distant galaxy like the one you see on the screen, when you look at a distant galaxy, it's taken a very long time for that light to reach you, so you actually are looking in the past. So it turns out that no matter where we look and how far we look in the past, it seems that there are certain regularities that always appear to be in operation, such as gravity. And so we call these things that seem to be always in operation laws, and we assume that that is true, that the universe is lawful, that it follows rules. But in point of fact, just to be honest with you, we can't actually prove it. Now, scientists investigate the natural world, and we believe that the universe is lawful, laws of nature, and therefore we try to explain things in terms exclusively of natural phenomena. We don't try to use magical or supernatural explanations. It's just the way we roll, you might say. We look only for natural explanations and natural causes in the sciences, and this, of course, includes chemistry. Now, what exactly is chemistry? Well, I would tell you, for starters, chemistry is kind of the in-between science. It's the science in the middle. But I want to make sure you understand explicitly what I mean by that. And so what is chemistry? How does it fit in relation to other fields of study? To help you understand that, I'm using a diagram here that's called a hierarchical pyramid. In a hierarchical pyramid, the various layers of the pyramid represent different objects or things or people or classes of things, whatever you want it to do. But it usually says something about the relative number and the position and perhaps how much power is being organized. So, for example, at the high school that I teach, the base of this pyramid, shown in yellow, might represent the students. It's the largest part of the pyramid. And of course, without the base of the pyramid, you couldn't have anything else. And so that might represent the students, because without the students, there wouldn't be any point in having anyone else there at that school. That's what school is for. It's for students. But we could also observe that students aren't actually very high on the power structure of a school. And so above them in orange might represent the staff, and then above that in green might be your administration, your VPs, your principal, and perhaps at the very top in the bluish green, that could be the administration for your entire school district, your superintendent, like my boss, Bob Nelson, or even the school board, the elected officials that are entrusted with administering the district. And so as you go up, there's less and less people who have more and more power. But of course, it all comes from the fact that we serve in order to benefit the students that are at the base of the pyramid. And so that's a way of describing the relationship in that particular diagram is called a hierarchical pyramid, and we'll use it again. But suppose we were to use this diagram with respect to chemistry. Well, before we even got into the pyramid, if we're talking about science, we'd have to first talk about math. Now, notice that math is not actually in the pyramid. Math underlies the pyramid. And math is an essential tool for science. It's not the same thing as science. There's parts of science that have nothing to do with math. But you've got to have some math to do science, because when we do experiments, in order for our results to be valid, we have to be able to measure them, and we have to be able to reproduce them, which means we have to use the tool of math. And so we use it for measuring basic quantities. And very clever people have been doing math for thousands of years. Science is a recent invention. That is, modern science is certainly recent. But math has been around a long time. Since the pyramid of science rests on math, you won't be surprised to learn that the base of the pyramid is very much like math. If you look at physics, physics often looks like applied mathematics. And one of the reasons there's so much math in physics is because physics really studies the basic things. It studies the most basic aspects of reality, things like matter, motion, and energy. And physics truly became a modern science sometime in the middle of the 17th century, when sufficient math was developed that we could actually describe these concepts in a rigorous way. Now, about 200 years later, chemistry, the in-between science, became a fully modern science. Now, notice the relationship between chemistry and physics. Chemistry is based on physics. And if physicists are interested in the basic things like matter and energy, chemists in particular are interested in the question, what are all the different ways that matter and energy can be arranged? Ultimately, that's what chemists care about. So chemistry is based on physics, and physics is based pretty heavily on math. And if chemistry became a full science, perhaps at the beginning of the 19th century, biology probably became a fully modern science sometime around the middle of the 20th century. Now, before that, there was some stuff in there that wasn't science, but it's a fully modern science. And biology and medicine and geology and many other fields of study are, to a large degree, based on both chemistry and physics. But chemistry is definitely the in-between science. It's the one in the middle that helps connect the math and basic concept of physics with other areas. And the way that chemistry does this is by emphasizing the role of the experiment. Now, chemistry itself is essential for modern life. We rely upon chemistry for various products. We have things like soaps, cleansers like ammonia, plastics like nylon or PVC, food items, and of course, fossil fuels, natural gas, gasoline, coal, and the like. Chemicals are said to be reactive. We all hear about chemical reactions. Most form of matter can enter into chemical reactions, though in this course we'll learn about forms of matter that really resist doing chemistry. But some reactions store energy by building larger molecules, and others release energy by breaking down molecules. When you store energy, you're making a chemical bond, which is a form of stored energy. And when you break a chemical bond, you release the energy that was stored there in the first place. Chemistry then focuses heavily on experiments based on those chemical reactions. And chemistry emphasizes the practical application of knowledge gained through this experimentation. And to do that, chemistry employs scientific method. Now, scientific method is an interesting thing because it's often taught in cookbook-like fashion. And we often use little tricks to remember certain steps. They do this thing first and then do this thing second. And so here's my trick. This is my trick. It's called oh heck. But oh heck isn't the last word in scientific method. In fact, there is no such thing as the last word. There is no such thing even as the scientific method. What do I mean when I say that there's no such thing as the scientific method? Well, a lot of times scientific method is taught like you were following a recipe in a cookbook. And people get the idea that if you do step one and then step two, you always do things in the right order, just the right way, like you're following a recipe, then you're doing science and you're guaranteed to be doing science right. Well, that's not entirely true. You know, just as one person in the kitchen could make a cake and someone else could follow that same recipe and they could get a different result, right? Just as there's no one way to make a cake, there really is no one recipe for doing science. And it often happens that they don't always happen. That is, scientific activities don't always happen in the order that you might see in oh heck. Nevertheless, oh heck, which is just an acronym, it's a phrase, a nonsense word where every letter stands for a word or a phrase. Oh heck is just my way of teaching the logic of how science works. And I want you to understand up front that this is not the only way it can happen. That logic can take other forms. So what is oh heck? Well, O stands for observation. H, a word that's probably very familiar to you, the hypothesis. E, the things we do to test our ideas, the experiment. And if we've done a good enough job that we actually can figure out what our result means, we have a conclusion. And if this conclusion is something that's fundamentally novel, something new, something important, then that would be worth sharing with the rest of the world. And so our last thing, K, is actually a phrase, knowledge sharing. Observation, hypothesis, experiment, conclusion, and knowledge sharing. Now, if that seems a little awkward at the end, it's because accounts of scientific method, explanations of how science works, often leave out the vital role that communicating scientific results plays in science. It's not enough to do an experiment. We don't do things on our own. The idea that significant science is done by one person in a laboratory in Transylvania that no one else appreciates or understands, that idea we often get from old movies, is really silly. Science is done by the scientific community, and very few good science is done by a few people. It's usually large groups of people interacting with each other that do important work in science. Now, what is an observation? Well, it's not just what you see. When we use the word observation, we often mean observe. We say, oh, we see something with the little sensors in our eyes, right? But the thing is about an observation, which could actually use other senses or could even use just reports of other people's work. The thing about an observation is that it's not just something that you notice. It's a phenomenon. The phenomenon comes from the Greek phenomenos, and it basically means this is something that makes you wonder why. So if you just notice something and you never think of it again, you're not really doing a scientific observation. But if you notice something and it makes you wonder why, then you're on the path to doing science. Because something amazing happens, even with a very small child. If someone wonders why, they may just get an idea. It may just pop into your head. It's kind of mysterious, really. It's a hard thing to explain, but an observation will often lead people to wonder, and as they wonder, they'll just get an idea. And the idea is just something that comes to your head from your imagination, really, to explain the phenomenon. So a hypothesis is really kind of a, maybe it's because, oh, I see this strange thing. I wonder what it means. I wonder. Maybe it's because. Ultimately, that's all a hypothesis is. Now, where the hypothesis is concerned, you may have been told something different by other people who were teaching science, or at least teaching a science lesson in elementary school. You might have been told that this is something that people only do after a great deal of study and research, and that you have to, read a bunch of really important stuff and learn a lot of things before you can do a hypothesis. But actually, that's not true. A hypothesis, a valid hypothesis, can come from any source. There are many cases in the scientific literature where a scientist was working on some problem and their child, their son or daughter, was with them and was looking at their work, and they just asked, a kind of naive, childish question like kids do. The kids don't know what they're talking about, but they just ask questions. And that different perspective that comes from the child inspires the scientist to think, oh, I wonder why. And they follow up on their kid's idea, and they try their kid's idea out, and they find out, oh, that was worth doing. I just learned something I didn't learn before. So you can get a hypothesis from any source. And if you can get a legitimate hypothesis from any source, that means you can get it from a small child. You can get it from someone who, is not very educated. So if you've been told that a hypothesis is an educated guess, that really is not true. It's just an idea from your imagination that potentially we could do science on. That's all it is. Now, why does this happen that many people have learned this kind of false, misleading definition? Well, it happens because a lot of science lessons are done in the elementary schools by well-meaning teachers who don't want to be overwhelmed with ideas from kids' imaginations. And so they say, well, students, what you need to do first is you need to do some research. You need to read this lesson and do this worksheet and watch this video. And maybe after a while, we'll let you do a hypothesis. And kids get the idea that, oh my gosh, doing science is so hard. We can't even do it yet. We're going to have to do so much before we ever allowed to actually do science. And that's really not true. You can do science anytime you want to, just by seeing something that makes you wonder why and thinking in a scientific way about it. So the key thing is not whether your hypothesis is true or false. The key thing is it falsifiable or non-falsifiable. These words do not mean true. They do not mean false. This is really important. If I say it's falsifiable, that doesn't mean it's true. It doesn't mean it's false. And if I say, that hypothesis is non-falsifiable, that also doesn't mean it's true or false. What does it mean? Well, it means that there's a way in principle to test the idea. There's a way in principle that you might be able to prove it wrong. It may be true, but if there's a way to test it to see if it might be true, then it's falsifiable. But if it's an idea that's not testable, that we can't ever, decide whether it's true or false based on an experiment, then we say it's non-falsifiable. You might say, well, that sounds strange. How could you have an idea that you couldn't test? But in point of fact, science is based upon natural explanations, and natural explanations have to have evidence. And if there's no way to get evidence that could potentially contradict your idea, then we say it's non-falsifiable. It might be true, but we aren't allowed to do science on it. And that's kind of sad. That sounds a little sad at first, like, oh my goodness, science can't do everything. But actually the strength in science lies in the fact that we don't try to do everything. Instead, we say we're going to study natural phenomena, we're going to propose natural explanations, and our ideas, in order to be called scientific, have to be testable. Let me give you an idea that's a hypothesis that's probably true, but which is very difficult to do science on. If you have a pet, say a dog at home, and you come home from school, the dog is often very excited to see you, right? Greets you at the doorway, barks, jumps on you, wants to lick your face, so excited because you've been gone the whole day, and now you're back and everything's wonderful. And you might get the impression from that dog greeting you with such excitement, you might get the impression that your dog loves you. And you say, oh, the dog's jumping all over me. My hypothesis is my dog loves me. And that's a perfectly reasonable thing to think based upon the dog's behavior. But it turns out that that is actually a very difficult idea to test. It's basically non-falsifiable because we could always imagine that the dog might be an evil genius who only pretends to like you so that you'll bring it food, take it out for a walk, and maybe pick up its poop so it doesn't have to. Well, that's probably silly. That's probably not true. The dog probably does have emotions and feelings, but there's actually no way at the present time for us to test that idea. That's a non-falsifiable hypothesis. Might be true, probably is true, but we just can't do science on it. And that's what we mean by a non-falsifiable hypothesis. The non-falsifiable claim may be true, but we are not allowed to use them in science. We're only allowed to use ideas that we can think of a way to test them. And if you're going to test them, it has to be a serious test. There has to be a possibility that your hypothesis will be falsified. Now, to speak more precisely, in chemistry, we treat the hypothesis as a tentative explanation for an observation, one that can be validated by experiment. Now, what do I mean by that? Well, the word tentative kind of means temporary. We pretend that the hypothesis is true. We pretend that the hypothesis is true, and then we design experiments to try to falsify it. Now, that may seem a little sneaky. I'll explain that in a moment. But we treat it like it's true for the purpose of doing science. And then we're going to test it with an experiment. And we're going to use observations. That is, our experiment's going to be intended to explain some observation. And then the experiment will be hopefully something that will give us some evidence one way or the other. So the experiment then is what we do to test our ideas. And scientists, as I try to suggest, we often attempt to falsify ideas rather than prove things true. A lot of people think scientists, we're spending our time proving things true. But a lot of times, that's not what we do. Instead, what we do is we pretend it's true, but we actually try to disprove it. Because it's actually a lot easier to disprove many ideas than it is to prove them true. Let me give you an example. Suppose someone has a hypothesis and they say, I think that all bananas are yellow. Bananas all over the world, every banana now, every banana in the past, yellow. Now that's actually a very difficult hypothesis. It's probably non-falsifiable because it's simply not going to be practical to go back in the past and try to find every banana of the past. It's probably not even practical right now to go through the entire world and say, oh, we're just going to keep checking the bananas to see if they're yellow. It's actually probably impossible that we could prove right now that every banana in the world is yellow. And, you know, it might always be that right at the moment we only see yellow bananas, but that doesn't rule out the possibility that we might find a banana that's not yellow. I can never really prove that all the bananas in the future are going to be yellow. But if I can find one banana, one group of bananas that's not yellow, I only need to find one group of bananas that's not yellow to falsify that hypothesis. So that hypothesis might be impossible to prove, but very easy to falsify. And you might say, well, that's sad. You're not actually proving anything true. You know, you're only proving things false. Oh, but actually in science, we like that, because when we test something like that and it doesn't pass the test, we can confidently eliminate a false explanation. And then we go back to the drawing board and we say, okay, this experiment showed that that explanation is not correct. What might be a better explanation? And we just keep refining it. And eventually we stumble on things that are hard to disprove, And then we start taking those ideas very seriously. So observation, hypothesis, which must be falsifiable, experiment, which must be controlled, and use good technique with accuracy and precision, such as significant figures. But if we go through all those steps and we get a result that seems meaningful, that we can report with some confidence, we call that a conclusion. Now, it often happens, you do an experiment, you go to all the trouble, and you get to this step and you don't have anything worth talking about. Well, start over. That's what happens in science. There's a lot of that. There's a lot of hypotheses that turn out to be false, or there's a lot of experimental results that turn out to be duds that don't prove anything, and you have to start over. I mean, science is hard. But every now and then we get a really good result and we say, okay, this is our conclusion. And the conclusion, usually very short, and all the conclusion is just what our results were and what we think they mean. Now, if this conclusion is not all that new, it's not novel, it's not earth-shaking, well, we might stop there. But that's not what scientists want. They really actually want to do an experiment that actually finds something new and something meaningful. And so if we get a result, if we get a conclusion that we think it is novel, it is new, it is meaningful, this is real new knowledge, then we have to do something. It's very important. We have to share our findings with the rest of the world. And so K stands for knowledge sharing. And we share it in many different ways. We write articles for peer-reviewed journals, and they go through a process where we actually have to prove that we did what we did before we get it published. We get checked by people. We make videos. We go out and do public appearances to make the public aware of the kind of science we're doing. Books, magazine articles, whatever way we can share that information. It's a strange thing, science, because, you know, scientists work in teams and they're often competing against other groups of scientists to solve some problem first. Everyone likes to be a winner. Everyone's competitive in science. There's a lot of competition. And yet at the same time, even though other scientists are our competitors, we are actually expected to share information, share data. And, you know, when we publish something new, we want our competitors to read what we're coming up with. And we actually want them to argue with us and disagree with us and try to prove us wrong. That's another really important reason why we share the knowledge. We're not just sharing it to help other people, you know, do the same science, but we're doing it so that people will go over our work and check us and say, well, this is good, but did you think about this? Oh, I see you got this number here, but how do you know that number's right? Asking those tough questions, having groups of scientists working on the same problems and challenging each other is really an important part of the scientific process. The knowledge that I share becomes someone else's observation. Hey, they found this. This is interesting. I'm not sure I agree. What does it mean? Ooh, I wonder why it's this way. Ooh, new hypothesis. Hey, we'll do an experiment a little bit different from the one they did and see if we can disprove it or come up with something else. In other words, the process goes on and on and on. Science is really effective, not just because there's a lot of smart, dedicated people doing it, but it's because the smart and dedicated people work in communities where they compete against each other, they challenge each other, and yet at the same time, they share data and cooperate. It's a very interesting experience doing science. Now, suppose we get a hypothesis that we keep trying to falsify, we keep trying to prove it wrong, and we just never get there. Does that mean we've proved our hypothesis true? Probably not. But what if we are really testing the hypothesis, and there's a whole bunch of scientists trying to prove it false, and they've done a whole bunch of different experiments to try to prove it false. After a while, we say to ourselves, we don't know if it's true, but we think it's probably at least close to the truth, or it might have part of the truth. If a result, we keep getting it, proves difficult to disprove, at some point it makes sense for us to take that idea very seriously. And we will take it so seriously at that point that we'll design our research programs around those ideas. We'll pretend they're true for the sake of discussion, and we'll treat this big idea that we're having a hard time disproving as if it's the center of all the work we're going to do. These powerful, useful ideas that resist our ability to falsify them are often called theories. Now, in everyday life, people use the word theory in a very casual way. They say, oh, that's just your theory, or that's only theoretical. And they use the word theory like it means a hunch or a guess or some idea that just came from your imagination. But of course, in science, we already have such a word. The hunch, the guess, the thing that came from our imagination, that's a hypothesis. A theory is not just a hypothesis. A theory is a hypothesis that we've tried to kill over and over again, and it keeps defeating our attempts to kill it. And so our definition of a theory is not that it's true, but that it's a well-tested explanation for a broad set of observations. Because when you try to falsify it many different ways, you try to disprove it with many different kinds of experiments, this has become a powerful idea because it doesn't just explain the original observation that made you wonder in the first place. It now explains all the experimental results you got, all the different ways you try to disprove it. It explains potentially a very broad set of observations. And so a theory is actually very, very powerful. And you'll now notice that I'm using the pyramid of science in a different way. The base of the pyramid is observation. There's no shortage of observations. And many of those observations will lead to a hypothesis that we'll attempt to test with an experiment. Most times the hypothesis fails the test and we eliminate a false explanation. But every now and then we get something powerful and useful that survives many different attempts to kill it, and it's a well-tested explanation, and we start organizing our research around it, and we call it a theory. And theories are actually the most powerful and most useful ideas in science. Not hunches or guesses, powerful, well-tested ideas that guide our research. Now here is the most powerful theory that's ever been developed in the history of the world. This is called the Standard Model of Fundamental Particles. Physicists have been building this model up out of bits and pieces for about 100 years, and the current version that we're looking at right now has been around for about 20 years. It's very complicated. It's got a lot of moving parts. It's got a lot of numbers in it, but it's extremely powerful. It makes more accurate predictions of more different kinds of phenomena than anything else that human beings have come up with. This is the model that's behind our understanding of the atom. Now, we actually don't know if this theory is true, but it's so powerful and explains things so well that we think if there's a better model, a better theory, it will probably include a lot of this model. In many cases, the model makes predictions that are accurate to 20 powers of 10. That is, it's 99.99999999999999999% accurate and precise. Wow. And you might think, well, that's pretty good. Do we need to do better? Has science already figured out all of the important things and there's nothing left to discover? Well, not quite. Even though the model you see here is the most powerful thing that we've ever come up with, we're busy right now designing our research programs around this model, and we're trying to kill it. We're trying to falsify it. Look here, you see this guy standing. He's standing in a gigantic machine, part of a gigantic machine. It is several stories tall, and this machine is part of a ring. The blue circle you see shows the ring, and this ring is a very large ring, and almost all of it's buried underground. So you have this machine that's several stories tall. And how big is the ring? The ring is more than 100 miles around. In fact, the ring is so big that it takes up parts of France, Switzerland, and Italy. This is the Large Hadron Collider, the largest and most powerful machine that's ever been built in the history of the world. And the only reason it's been built at a tremendous cost is to test the Standard Model. Why do you have to have such a big machine? Because the Standard Model is already super accurate, and to test it, you need energies. You need to be able to simulate energies like that, like those energies that were present at the Big Bang, the event that created our present universe. It's kind of awe-inspiring. But just keep in mind that even though we figured a lot of things out and whatnot, we're actually trying to break the best thing we came up with. And that's not what people expect to hear from scientists. They expect to hear, oh, we've got the facts, we know everything, and we're satisfied. Well, we're pretty good at what we do because we insist on natural explanations for natural causes. But we don't stop. We keep challenging ourselves, and we keep trying to push forward and come up with things that are better. And every now and then we come up with something truly revolutionary, and then that field of science changes in a profound way, and then we go after the next problem. So, observations, hypothesis, theory. Have we left anything out? Well, probably a whole bunch of you have probably said, well, what about those natural laws that you mentioned? Aren't laws more powerful than theories? Well, they are very powerful, but they're not as useful as theories. So let's understand how a law differs from a hypothesis or a theory. A hypothesis, again, is just an idea from your imagination that we try to falsify with an experiment. A theory might not be true, but it's a pretty powerful explanation for a lot of things that we haven't been able to falsify yet, and we organize our research around them. So what's a law? Well, a scientific law is a generalization. It's a general statement. It's not a specific statement. It's a very general statement that's very powerful, but it doesn't actually explain anything. It's a general statement that says, we found this one thing that seems to be true everywhere that we look in the universe. It doesn't explain what we see. It just says we see this general rule. Like, for example, gravity seems to have the same action no matter where we look with our telescopes, no matter how distant or far back in the past, we see the effects of gravity throughout the history of the universe. Okay, so we say there's this phenomenon that must be universally true, and we say its full name is the universal law of gravitation. But that doesn't actually explain it, it just describes it. And the most efficient way to describe a scientific law is not to write a sentence. It's actually usually to have an equation, a mathematical expression. An expression of something that, as far as we can tell, is always true all the time, everywhere in the universe. So there aren't a lot of laws in science, and you definitely have to take the laws into account because they're telling you something that seems to be generally true everywhere in the universe. You've got to account for it. But it doesn't explain why the law is there in the first place. It doesn't explain the phenomena that we're trying to understand. It simply gives us a tool for saying, okay, well, we think this is true, so therefore our explanations have to agree with the physical laws that we observe. The main thing laws do is they put limits on what kind of explanations we're allowed to propose, but they're no substitute for a hypothesis, and they're definitely no substitute for a good, powerful theory. So there you have it, observation, hypothesis, theory, and laws, and we use a series of steps in OHEC to describe how science is done. And ultimately, in physics and chemistry, there aren't a lot of physical laws, but whatever we see, they're true for the entire universe. The entire universe, as far as we know at the present time.